Welcome to the AICE Chemistry lecture series. Today we're going to go over chapter 3.8, which is the last section in chapter 3. And we're going to talk about calculating reactions that involve gases. So making calculations involving gas volume specifically. Now this is a pretty short section. Why? We are going to discuss calculating volumes of gases using room temperature and pressure, what we now call standard temperature and pressure in Cambridge. That means 25 degrees Celsius and 1 atm of pressure. This is not the extent of volume calculations for gases for AICE Chemistry. However, this is all we're going to discuss because this is as much as we discussed in honors chemistry. In chapter 5, we're going to go ahead and discuss a much more wide topic, which is the calculations of ideal gases in non-standard conditions, not under r.t.p. or room temperature and pressure, essentially. But that's a much bigger conversation we're going to have in chapter 5. For this chapter, we're just going to discuss these conversions under room temperature and pressure. So let's get into that. And all of this is going to be based on what we call Avogadro's hypothesis, which is something that we talked about last year. Avogadro's hypothesis is that at room temperature and pressure, 1 mole of any gas is going to have a volume of 24 cubic decimeters. So it doesn't matter what that gas is. This is any gas. It could be carbon dioxide, oxygen, hydrogen, methane, ammonia. It doesn't matter what the identity of the gas is. If that gas is under r.t.p. conditions, the volume of that gas, what we call the molar volume, the volume of 1 mole, will be 24.0 cubic decimeters. So the conversion of 24 cubic decimeters per mole of gas is known as the molar volume. And we can use that number for very important conversions in chemistry as long as we have room temperature and pressure. The minute that the temperature is not 25 degrees Celsius and the minute the pressure is not 1 atm, that number is no longer valid. Again, room temperature and pressure means 25 degrees Celsius of temperature and 1 atm or 101 kilopascals, which is a different unit of measurement for pressure. All right, that's a 1 or a no. So 1 atm or 1 kilopascal or 101 kilopascals of pressure, 25 degrees Celsius of temperature is our room temperature and pressure. Under these conditions, 1 mole of any gas will be equal to 24.0 cubic decimeters in volume, but only under these conditions. So we have that right here. Mole of gas, what we call the molar volume, is that the moles of gas is equal to the volume of the gas divided by 24 dm cubed per mole, meaning 24 cubic decimeters of volume per mole. That means that we can calculate the moles of a gas at r.t.p. by grabbing the volume of that gas and divided by 24. Or we can calculate the volume of a gas at r.t.p. in cubic decimeters specifically by multiplying the moles of the gas by 24.0. And you can tell that these units are going to cancel, right? How do we get moles here? Well, if we got dm cubed and we divide it by dm cubed over moles, the dm's cubes cancel out and we end up with just moles. If we want the volume of the gas in cubic decimeters, then we multiply the moles times the molar volume, dm cubed over moles. The moles cancel out and we end up with just cubic decimeters. So that's, we can see the math work out in those units. And that's very important because a lot of the time in these math problems, throughout this chapter, not just in this section, but throughout this chapter, it's very complex math problems. Whenever we get lost in them, we can always look to the units to help us out, to guide us in the right direction. So if we remember the equations, we look through units, we can use those to help our critical thinking and figure out what the steps to take are in order to get somewhere. And that's why I always urge you, whenever you're doing this math, whenever you're writing math down, to look and put the units in your work because it'll guide you in the right direction. But let's put this into practice. So that's all this section is. It's this hypothesis, this equation of most of a gas is equal to volume of a gas divided by the molar volume. Or volume of a gas is equal to most of the gas times the molar volume. That's all this is. But let's look at a problem, because while you look at this problem now in the next slide, you'll see how complex these questions can seem. So let's look at this question. This is from paper 2. So here we have the compound As2S3 is a common mineral. Again, do we care it's a mineral? Not really. When As2S3 is heated strongly in air, it forms a mixture of products shown. So they give us an equation. We have As2S3. Now, have we ever seen this this compound? Have we ever worked with this compound? No. But as we read this, you'll realize that's not the point here. The point is not to look at this compound, to work with this compound. The point here is going to be that we should know how to do the math in this compound. All right? So, if we keep reading here, we have 2As2S3 solid plus 9O2 oxygen, essentially gas, yields As4O6 solid. Again, we've never seen this before, but doesn't really matter. Plus 6SO2, or sulfur dioxide, gas. Now let's keep reading to see what exactly we're supposed to do here. And I'm going to bring this over here so we can start using my highlighter here. A sample containing 0.1898 grams of As2S3. So I'm going to highlight this because we'll probably need this number later. Maybe a little too much highlighting, but that's okay. Is placed in 0.1 cubic decimeters of pure oxygen in an excess. Which is an excess, sorry. So the 0.1 cubic decimeters of oxygen is an excess in a reaction chamber connected to a gas range at room temperature. Again, the second part, we don't really care too much. We know we have 0.198 grams of the As2S3. We know we have 0.100 vm cube of the oxygen. And we know that that oxygen is in excess, which might be important. Remember our conversation about excess reactants and limiting reactants earlier in this chapter. The reactants are heated until no further change is observed. So this is important because no further change is observed means that we have reacted as much of this as we're going to react. And because they told us, and we know that the oxygen is in excess, what this no further change is observed tells us is that this As2S3 was completely reacted. We had completely reacted that large amount of As2S3. The products are then allowed to cool to room temperature. Okay, so we're going back to room temperature, which is good because we can use that 24.0 dm cubed per mole. Calculate the volume in cubic decimeters. So this is what we want to figure out. The volume in cubic decimeters of gas present at the end of this experiment. Now this is where the critical thinking comes in, because it's not just of SO2, it's not of O2, it's of gas. Meaning we have to think about, okay, what are the gases here? What are the gases in this reaction? Now, obviously, one of the products is SO2, and that is a gas, right? So that's what you're going to be tempted to figure out. You're going to be tempted to figure out the amount of SO2 that we have created and then give that as an answer. But you have to remember, the oxygen is in excess, meaning that we are going to have some of this oxygen left over. Meaning that when we're talking about the gas left over at the end of the experiment, we're not just talking about the amount of SO2, we're also talking about the amount of oxygen left over. So we're going to go into that as well. The molar volume of gas is 24 cubic decimeters per mole under these conditions. Assume that the pressure is constant throughout the experiment. Great. So we know that the oxygen is in excess. We know how much As2S3 we have. And we know we need to, at some point, use this molar volume we were talking about. So let's put all of this together. Now, this is where things get hard, because we need to keep track of things. what I like to do to keep track of things is to put these numbers on top of where they belong. So we know we have 0.198 grams of this As2S3, and we know all of that is used. We know we had 0.100 cubic decimeters of oxygen, and we know that's in excess. So what are we trying to find here? We're trying to find the amount of SO2 that was created and how much O2 is left over. So let's start with the easy one, which is the amount of SO2 created. So we know we are going to use all of these 0.198 grams of As2S3. So whenever we have a limiting reagent problem, we always want to use the number of that limiting reagent to do all our calculations, because we know that that is completely used up. So we have 0. So we're going to first calculate SO2 amount. So we're going to put here SO2 question mark, and we'll do this in red. So we have 0.198 grams of As2S3. Obviously, the first thing we want to do is transform this into moles, because we never want to work with grams. We always want to work with moles. So we're going to need the molar mass here. So I'll bring over my periodic table. Oops. So we have, I'll write it up here so it carries over to the back end. So we have As2S3. Molar mass of As is here is 74.9. Molar mass of sulfur is here is 32.1. Times 2 for this, times 3 for this. That's going to give us 74.9 times 2 is 149.8. Oops, 149.8 plus 32.1 times 3. That is 96.3. And then we add those up to get the molar mass of the whole compound, which is 96.3 plus 149.8 gives us 246.1 grams per mole. This is the molar mass of the As2S3. So retire this periodic table here. And we have that number there, so we can work with that. So we know that molar mass of this is 246.1, so we know that 246.1 grams of As2S3 is equal to 1 mole of As2S3. Now remember, the goal here is to figure out the amount, and they want to calculate the volume, so that we want the volume of SO2. So we'll put here B of SO2. So we need to convert this now from As2S3 to SO2. So we know from the coefficients that 2 moles of As2S3 is equal to 6 moles of SO2. Now here's where it gets to the point where we have transformed it now to the SO2 which we're looking for, but we also need to keep in mind that we want volume. So how do we convert moles to volume? That's where this molar volume we just learned about comes in. We know that for every 1 mole, any gas, doesn't matter if it's SO2, O2, or what, occupies 24.0 cubic decimeters. So we know that 1 mole of SO2, because SO2 is a gas, will occupy 24.0 cubic decimeters. This is where you have to be careful. This is a gas, so we use the 24.0 cubic decimeters per mole, not the concentration. Concentration is used per cubic decimeter of a solution, not of a gas. So always remind yourself, what am I working with? Am I working with a solution, in which case volume we will use concentration, or am I working with a gas, in which case, at room temperature of course, in which case I use the 24.0. So we can now figure out the volume of this SO2 that I made. So 0.198 times 6 times 24 divided by 246.1 divided by 2 is going to give me a total of 0. And we're going to keep it to 3 sig figs because that's the number that I was given here for my initial number. 0.0579 cubic decimeters of SO2. And that's my first part for this question. This is the amount of SO2. Now, you might be tempted if you don't actually use your critical thinking. You might say, okay, that's the volume of SO2. That's my final answer. But you got to be careful because, again, the question is not how much SO2 is created. The question is how much gas is present at the end of the experiment. So you have to ask yourself, what gases are there? There's the SO2, but there's also the O2. And we have to remember that we did not use all of that O2. Again, the oxygen is in excess, meaning that we're going to have leftover. So we're going to now use a different color. We'll use blue. So now we need to figure out the volume of O2. And now that's going to be a very similar process, but we need to take a slightly different approach here because we can use the same approach of using the AS2S3 to figure out the amount of O2 that we used. And then, since we have the amount that we started with, we can figure out how much is left over. So let's do that. We're going to have here 0.198 grams of the AS2S3 over 1. And again, we want to work with moles, so we're going to use molar mass and turn it into moles. So 246.1 grams of AS2S3 is 1 mole of AS2S3. And now that we have the moles, again, we can use a mole ratio here in the equation, a 9:2 mole ratio, to convert AS2S3 to moles of oxygen. So we know that 2 moles of AS2S3 is equal to 9 moles of O2. Once we have that, we can, just like we did with the sulfur dioxide, we can now convert these moles of O2 to cubic decimeters of O2. Because again, it's a gas. Doesn't matter whether it's O2 or SO2. A gas is a gas, meaning we can use this 24.0. 1 mole of O2 is 24.0 dm cubed of O2. So we do the exact same measurement or exact same equation that we made for the SO2, but you have to be careful with what we do with the number. So we're going to do the math. So we have 0.198 times 9 times 24 divided by 246.1 divided by 2, and we get that we have 0.0869 dm cubes of O2. But you have to be careful. Here's where this differs from honors chemistry. Honors chemistry, you just did math. You didn't think. Here, you have to ask yourself, what is this number? Yes, it's dm cubes of O2. It is volume of O2. But what about it? This came from the limiting reactant that we used. So that means that this much AS2S3 needs this many dm cubed of O2 to react. Meaning, this is 0.0869 dm cubed of oxygen used. This is how much oxygen we used. Notice that we're calculating how much gas is present at the end of the experiment. Meaning we don't want to know how much oxygen we used. We want to know how much oxygen is left over. In order to calculate how much oxygen is left over, if we started with 0.1 dm cubed, all we have to do is say, okay, then if I started with, I'm going to put a little arrow here. If I started with 0.100 dm cubed of oxygen, this is how much we started with, and I used 0.0869 dm cubes of oxygen, so this is used, then what I have left over is 0.1 minus 0.0869, which is 0.0131 the cubes of O2. This is how much is left over. And you have to think about that because otherwise you're going to use a 0.0869 and that's how you end up with the wrong answer. So now we know that we have, let me use black now. So we now know that we have 0.0131 dm cubes of oxygen left over at the end of the reaction. We know we have created 0.0579 dm cubes of SO2, which are the two gases in this reaction. So how much gas is present at the end? Well, all we have to do is add up these two numbers. We're going to do 0.057, oops, let me clean that up a little. 0.0579 dm cubed of SO2 plus 0.0131 dm cubes of O2. Again, this is created. This is left over. But again, because this was created and because the other one was left over, they're both there at the end of the reaction. And then if we add those up, 0.0579 plus 0.0131, that gives me a total of 0.0710 dm cubes of gas in total. And that is my answer. So you can see how what we learned here is a very small amount, right? It's a very tiny equation, which is this right here, the 24.0. But you can see how it can be incorporated into a much larger problem. And I want to go back to our problem. So this is what we ended up with. That 0.0710. And know that that number might end up being slightly different than what you see on the mark scheme. And that's mainly going to be due to rounding error and stuff like that. But it should be very close. So let's look at the mark scheme now. So this is a mark scheme. And you can see how this is a very chunky question. This is a 4-point question because it does cover a lot of steps. So we get 1 point for figuring out the moles of As2S3, which we do by grabbing those grams, dividing it by 246.1 in order to get our moles. Now, you don't actually need to show this. You don't need to show the answer, which is what this is. We show that in this step right here. We have that 0.198 divided by 246.1. We're just not showing it as a separate step. Then you get another point for the moles of SO2 using that limiting reactant that we just talked about. So for calculating the moles of SO2, which again, we don't do directly, but if you're doing scientific notation, you calculate right here in this step. Because you calculate the moles of As2S3 first and then the moles of SO2. So you will still get credit for that step right here in the stoichiometry. And then for obviously turning those moles of SO2 to the volume of SO2, which we do at that, this right here. We do that in this whole red section. We calculate the volume of the SO2. So that's another point. So this red section that we just saw, that gives us 2 points. Then there's a third point for moles of O2 used in the reaction, and then the volume of O2 used in the reaction, which is that blue section in our work. So we get another point down here for converting from grams of As2S3 to moles of As2S3, then to the moles of oxygen, then to the volume of oxygen. So this step right here, this is another point. So we have here, and I'm added in. Let me use a color I haven't used. We'll use rainbow. So we get 1 point right here for this conversion from here to here. We get another point for this answer right here, the volume of our SO2 that's created. We get another point right here for figuring out the volume of O2 used. And then we see here the last mark, final total volume of gas. The 0.1 minus a 0.0869 of the oxygen, and then adding that to the SO2. So that whole step is our last point, and that's 0.071 is what we get. Now notice how they put 0.071 and the 0 in parentheses. What that means is that you don't need that 0. If you put 0.071, they'll give you the points. That extra 0 though is needed if you're using significant figures, but they're not worrying too much about significant figures. You can still get that point. You'll say here, only award fourth mark if the final answer rounds to 0.071. Answer to a minimum of two significant figures. I mean, you needed to use two significant figures. If you put here 0.07, you won't get this final mark. Notice it says a minimum of two significant figures. But your answer needs to round to this if you are using that extra decimal. So you can see how our answer did round to 0.0710. So anything from 0.0710 to 0.0714, you will still get the point, because it will still round to 0.071. But yeah, so that last point here is for this part right here, for adding all of this up, this included right here, and getting that final answer. So that's 4 points, because it's a very lengthy question, so it's worth a number of points. And it does require a lot of critical thinking. Notice they do make accommodations for different things. It says, for example, max 3 for using ECF from M1 to M2 to M3 and M4. Meaning, what does that mean? If you, let's say, do one of these early steps wrong and you don't get 0.1 or 0.2, you can still get the rest of the points up to 3 total marks, as long as the rest of the work is correct. So even if you messed up this first step, or maybe the second step, you could still get the rest of the points and get a maximum of 3 marks. And then you can see here at the end, award all 4 marks if final answer rounds to 0.071. Now, what does this mean? This does not mean you can just put a number and forget about your life, right? You don't need to not show any work. What this means is that there are other ways of approaching this question and this problem. And if you use one of those alternate ways, if you do use some other way to show your math that still makes sense, that is still appropriate math, as long as your answer is still correct, they will give you full credit. They will give you all 4 marks for this problem. All right. So this is a perfect example of a very, very critical thinking heavy problem where you have to incorporate all kinds of stoichiometry, mole conversions with molar masses. You have to incorporate a stoichiometry of conversions from one chemical to another. You have to incorporate limiting and excess reactants, the volume conversions for molar volume, and then a lot of just heavy critical thinking for those gas present and all that kind of problem. So this is what you need to start getting used to. Now, this is a very high level critical thinking problem. There are easier ones, but this is kind of like the holy grail, right? 4 points. You don't want to miss out on these points. And once you understand it, it's a pretty straightforward problem. All right. So that's it for section 8 of chapter 3. And now this is it for chapter 3. And this problem is just really a great example of what chapter 3 is all about, right? Because we didn't learn anything new. Everything we covered in chapter 3 you knew from AS chemistry, or from honors chemistry, but it's all about how do we think about these problems, how do we approach them, the critical thinking, and not falling into despair, not seeing these problems and just saying, oh my God, I can't do it, I'm not going to be able to figure this out, I'm going to fail, but saying, okay, let me take it one step at a time. Let me circle or highlight all my numbers, let me figure out what I have, let me look at the units, and how can I get there? What does each question mean? What does each problem mean? So on and so forth. All right. So my last kind of words for chapter 3, don't fall into despair. You can do it. Use your critical thinking, and you will eventually arrive at the answer if you look at your units. Thank you very much, and I'll see you in chapter 4.